Hi everyone, I'm Caleb,
I'm Felix.
I'm Evan.
and today we're going to be looking at an extended branch of calculus known as line integrals.
What is a line integral? A line integral is an integral, a general formula that will give you the area of a 3D shape. And this shape is created using a parametric function, x of t and y of t, that will create the base of the shape, and a corresponding f of x of t and y of t function, which will spit out a corresponding z value for every xy pair, and subsequently will make a 3D shape like you see in the diagram to the right. Um, and so how are we going to find the area of this shape? Well, of course, using an integral. So here at the top right, you can see the general form of the integral that will give you the area of a 3D shape. And you can see it has the bounds from t equals a to b, f of x of t, y of t, which is the function that spits out a z value. And then it's in terms of ds. ds is the infinitely small change in the distance along the xy parametric curve. Um, so instead of using, for example, dx like we normally would, we just use the change in distance along the base of the thing. And so you can see how the change in base times the height for the entire shape would give you the area of the entire shape. So unfortunately, in that form, we can't actually evaluate the integral because we need everything to be in terms of t in order to do that. So to fix this problem, we can rewrite ds using the arc length formula, which we're already familiar with, but here's a quick derivation. We start out with the square root of the change in x squared plus the change in y squared. That's just the Pythagorean theorem. And we multiply it by the change in t over the change in t, which is, of course, just 1. And we can move 1 over the change in t into the square root, as you can see in the next step, leaving dt on the outside. And then finally, we can do a little bit of algebra to rewrite it and get it in this form here, which is the change in x in terms of t squared plus the change in y over the change in t squared dt, all squared.
Okay, and this is the final formula. And so it's probably a little easier if you do a practice problem. So it's like, I'm not going to like go over it super in depth because that's not really what the presentation is about. But just to like give a more like concrete example. Um, so, so here we got we're just gonna like have some stuff plugged in for x, y, and our parametric functions. So instead of dx and dy, we have actual x and y values. So x is cosine of t and y is sine of t, and our f of x y is just going to be x y, and that gives us our z value. And our t values are going to be 0 and pi over 2. So if you plug all that stuff into the formula, you get xy and then just the generic dx dt stuff. But then if you plug in cosine t for x, sine of t for y, and then you take the derivative of x and y, you get this whole business. And then taking the integral isn't that bad because cosine squared t minus sine squared t is 1. And so you end up just getting cosine t sine t dt, and the integral isn't that bad. You can use sub it pretty easy, and it ends up working out to 1/2. So that's a more concrete example.
So, we've looked at what the formula is, how we get there, and how we can use it, but how does this actually help us? Well, line integrals are really crucial in electromagnetic physics, which is one area that many of us are even studying right now at school. And one of the fundamental laws in circuitry is Ampere's law. And Ampere's law states that the permeability multiplied by the current in a closed system where we have a loop of electricity. is actually equal to the magnetic field times the respective element length that is traveling in the direction of the field inside that closed electric circuit. So Ampere's law is actually made possible by the line integral, which is pretty implicit. But taking a closer look at the image below, we see that we are taking a line integral at the edge of the closed loop, and we're taking it with regard to the current that's flowing through it, as we stated before. And the line integral for the magnetic field that flows about the closed system is actually equal to the sum of all of the current inside the enclosed system. And this is really, really important because when we're making things like, phones, laptops, where we need to have lots of circuitry going on, we want to make sure we don't have, too much current or too much magnetic field that's going to interrupt important, like radio waves, things like that. So we have to actually apply the line integrals to ensure that we have, equal proportions for everything. So yeah, that was our quick lesson on line integrals, and thank you for your attention.